discovery discussed on Monday morning that a bunch of us all got up really early, went up to the lab to watch the news being broken and to discuss the papers and see whether we believed what we believed or not. And so I don't know when people saw the front pages all had titles like this: "Space Ripples Reveal Big Bang Smoking Gun," which somehow seems to tie to the previous discussion, the smoking gun. So I thought, if partly just because I thought people might be curious, I would describe what it was that was announced on Monday. I don't know how many people already have been reading about it and listening to it. A quick show of hands for who's been looking into it. Fair number. So let me describe what was that was going on, and I also want to point out that it really ties in remarkably well with the end of our discussion. Did we just show something? No. Hello? All right, so where are my PowerPoint slides? We'll do it for a second. Okay, right. So this ties into the to this this point that we finished the last class with, which is this problem of how do you know what to believe when an article shows up in the newspaper in this case, or in a scientific journal, which we then all downloaded from the web, and we all were sitting around all morning Monday at 7:30 in the morning discussing the the content of the article and trying to figure out how do we know that we believe it any more than the editor of New England Journal of Medicine is believing most of what's been published in her journal. So I started to think about it, and I was realizing, okay, what we were thinking about is, in this class, we've been starting to present a whole bunch of ways to approach the world, and that are supposed to help you when you see a new paper, a new article show up. And I started going through this list, and I realized that with the possible exception of these two over here, I think almost every one of these was in play on Monday when we were all sitting around the room talking. And so let me walk through what it was that we heard about, and then as we go, or afterwards, both, I think you'll see almost each one of these things in the discussion as we were trying to figure out whether or not what we made of this article. Because the problem is, this was a really exciting result, and if true, this was going to change a lot of what we were thinking about. If not true, we want to know. So first of all, what was this all about? So there are these experiments that they're doing down in near the South Pole. Actually, the South Pole is about 50 meters that way on here, and these are these shields around telescopes. That's one, and that's another telescope, both of which are being run by friends of mine, people I know. And they go down, they fly down to the South Pole. It takes a long time to get there. This one's the South Pole Telescope, which is primarily, the detectors are primarily built and designed by people right up here in the physics department. This is the one, however, that had this particular result. This one's called BICEP2. And inside that shield, which just keeps the anything from bouncing off the ground and going into the telescope, you have something that looks like this. That's what it looks like. So you're looking out of a hole here in that shield, out into the sky, and then in the back is a telescope. It feeds into a detector system which has electronics down here, and they scan the sky. And what's different from the most telescopes that you might come across. Is that this is not a telescope that's looking in the optical wavelengths. So we get to see stuff that's visible to the human eye, and that means that it has a certain wavelength of light, and that's around. If you actually think about how big the size of the wavelength is, around the size of protozoa, these little amoebas and things of that sort. There's higher energy light that's shorter wavelength that our eyes don't see. That's ultraviolet light that gets us sunburns, and that has wavelengths that are the size of molecules. There's longer wavelength light, which we also do not see, which is the infrared light, and that's when you hold your hand over a light bulb here or something like that. You feel the heat. That's actually infrared light hitting your hand, but we don't see it. and that's a longer wavelength where the little waves of light are around the size of the tip of a needle. But if you go even longer, yeah, okay, tip of the needle. If you go even longer wavelengths, so these are even less energetic waves. You get to microwave area, and you all have microwave ovens. At the short end of the microwave here, so it's basically millimeter size wavelengths, the wavelength of light. That's what this telescope was designed to look for. And the reason is because this is what is left over from what was the original glow at the time of the Big Bang. And I'll show you where that's coming from. But there was a lot of very hot, dense plasma in the early stages of the universe, and it sent off this heat of these photons started traveling out that actually began somewhere further back, closer to the visible as a glow that you could have actually seen if you could have been there at that time. And then the universe expanded, and it got stretched and stretched and stretched, and the energy got diminished and diminished, while the photons have been traveling and going all around the whole universe. And if you look in any direction, you'll see photons that are still struggling to get to you from any possible direction, but they're now degraded. They're stretched out to being this microwave wavelength of just about a millimeter. And so any direction you look in the sky, you'll see those photons still coming in. And so people were really curious to know, well, can we actually pick that up? And back in the late 60s, they first started to see it. Originally, actually, I thought it was noise, to mention the noise, and they only later spoke to one of their colleagues at the next university and realized that it actually fit very well, not what they expected to see, the characteristics of noise of this particular instrument they were using at the time, but it was actually this glow left over from the Big Bang. So since then, there have been many, many generations of experiments that have not only detected this glow left over in any direction, but start to map it out. You ask, well, is it the same there and there and there and there and there and there? And if you look across the whole sky, nowadays using satellites to do a really deep scan of the sky. So this is the most recent one, the Planck satellite. The first one that did this actually was the Kobe satellite that George Smoot got the Nobel Prize for here at Berkeley as well. So we're written all over this field. This is a real Berkeley product. In fact, the people whose announcement you heard about on Monday were the descendants of Berkeley faculty who've now gone off into the world and populated it with CMB studiers. So if you look up in the sky, you see something that looks like this. If your eye was able to pick up these microwave radiation, and if you could recognize slightly hotter spots and slightly cooler spots, and that's what you would see on the sky. And this is a very tiny difference. In fact, the glow is this very uniform glow, and this is magnifying the differences. So these are apart in 10 to the 5 that you're seeing differences here. And so for many, many years, all people knew about was this very, very uniform glow. And they kept saying, I think there's some reasons in our current theories of how this stuff got there that you might expect to see some little differences across. And they would build another generation of instruments that was able to go be a little bit more sensitive to look for the differences, and they didn't see any differences. And then they built another generation that was maybe 5 times more sensitive, and they didn't see any differences. And they built another generation that was 10. I mean, this went on for. And so this is a clear example to me of scientific optimism, because they thought that this was worth sticking to the problem, and they did it for generation after generation until they finally started to see these differences. Actually, the whole thing is an interesting example of the question of is this a question that can be answered by science? Is it even plausible that you should be asking questions about how the universe got to where it is today by going out and doing measurements? And it's remarkable to me that you can actually even do these kinds of measurements at all. And the fact that you do them could have some bearing on this question of how did the universe get to be where it is today, which you might, at one point in fact, most of history, you might have thought was a question purely for religious figures or philosophers. And so the fact that we've turned it into a scientific question is already interesting. The fact that we're measuring something that our eyes would not detect is a question for this class. And we've now gotten so used to using these that the fact that we're measuring infrared light or ultraviolet light or anything like that is anything different than if we held up a meter and measured the light from that light bulb. We treat them all as if they're all the same thing. The amount of reality that we attribute to it is almost exactly the same. So from the working life of most scientists working with this stuff, they don't even ask the question anymore as to whether these hot and cold spots are real or whether they're somehow the figment of our instrument. So it's clearly part of that same story that we talked about at the beginning. Now, this particular telescope I'm showing you here was scanning the sky in just a region of space that was of this field here that's drawn on the sky here. That's just chosen as being a fairly clean region. It didn't have much of the galaxy. You can see lots of structure comes from the galaxy. We don't want to, in this case, we don't want to study our own galaxy. We want to study what happened way back then at the time of the Big Bang. So this is all in the way. So you try and choose a place that's fairly clean with low galaxy light. And in that little patch, the first thing they show you, and this is from the paper, by the way, that came on Monday. The first thing they show you is this is the hot and cold spots in that little patch on the sky that we already saw in the satellite picture I just showed you. So nothing really new there. This gives you a sense for the differences of hot and cold. These are measured now in microkelvin. It's around, all this glow is now about 2.7 degrees in Kelvin, meaning just above absolute zero. So it's a very little bit of temperature, a very low temperature. And then these are little differences at the hundreds of microkelvin range. I was saying you've got to get down to sort of 10 to the minus 5 range before you can trust that you were seeing these differences. So this was a tour de force just to get this at all. However, they weren't actually looking for that anymore, because this they already knew. What they were looking for was a polarization in the light. So they wanted to be able to see if you held up a polarizer, this way or this way. If you held Polaroid glasses up, this way or this way, do you get a different result? And there are reasons why you might expect there to be polarization of this light. Now, that is an even tougher measurement, because to measure the polarizations, which is what these are showing, you have to get down not at hundreds of microkelvin, but single microkelvin, and these are the easier ones. The ones I'm about to show you in a minute are 10 times better than that. So they had to do something that was almost 1,000 times more precise than the amazing tour de force of getting this far in the first place. So this is impressive scientific optimism that got them to this stage. So why do they think that there could be polarization? And why is that relevant to our history of the expansion of the universe? Well, first of all, the picture that we're working with today of the universe, and I can tell you more about why we think of it this way, is that there was this very hot, dense moment that we can't think earlier than yet, which is what we're calling the Big Bang. And the question has long been, if you get sort of fluctuations in whatever that cosmic soup was at the time of the Big Bang, how come we can't see very big differences in that cosmic ray background over there and over there and over there when we look at different places in the sky? That place in the sky is too far away from that place to ever talk to each other in the whole lifetime of the universe. So how could they agree to set their brightnesses in the same place? And there was a theory that was put forward just when I was in college called the inflation theory. And I remember being really excited and going and hearing this new idea being put forward. I'm sorry, this was when I was in graduate school. All the physicists went to hear these talks. And the idea was that you take things that are close enough to each other to talk, and to sort of even out their temperature with each other, and then you expand it. Now, you don't just expand it a little bit, you expand it a lot. And then you expand it again, and then you expand it again. And it's exponentially expanded by trillions and trillions of times, so that you've taken what was a little speck that was closely in communication with each other. Now there's another little speck over here, close communication, and another one over there. But this little speck is now huge. It's the size of our entire universe that we get to see. Now there's, the neighboring place also expanded, and so there's a bit of the universe we don't get to see, and there's another neighboring place over here that expanded that we don't get to see. But the part that we're familiar with, our friendly local huge universe, came from this speck that was in communication, and that's why we think it's as uniform a glow as it is. It also explained a few other things at the same time. Great theory, but how are we ever going to know whether that really is the reason that occurred? And people have been playing around with It's a tough one to beat, by the way, so people have a very hard time coming with alternative theories, but there are some that we'll be trying. There's one of my good friends at Princeton, Paul Steinhardt, has been saying he doesn't think this inflationary theory is right, even though he was one of the people who created it. And he thinks that you have to, what you probably will end up needing to do is have multiple expansions, and then you reset things in another expansion, and you reset things in another expansion, and that achieves things in a different way that he'd like better. It turned out that theory of Paul's and the original simple inflation theory that he was also responsible for make different predictions about that polarization that I was about to describe to you. So people were in an interesting situation because they said, if we could just measure that polarization, which is, a million times harder than just measuring that glow at all, maybe we can start seeing whether or not there's any reason to believe this inflation theory versus, for example, the cyclic theory that I was just talking about. The idea is that in this inflation theory, you can actually make some estimate of what happens with the gravitational waves. These are waves in the actual fabric of space itself that travel out with carrying this pattern left over from the original differences in this cosmic soup. Those waves are very weird waves because they actually are of space itself. When waves travel through space, it's not like the waves that we're used to seeing in water, which just go like this, traveling along. It's not like, which is also similar to what electromagnetic waves look like, just a wave that travels to you, in a very dimensional way that we're used to visualizing. Waves in space do something bizarre. They stretch space this way while they compress it this way, and then they compress it this way while they stretch it that way, and they travel along, compressing and stretching in opposite ways. And let me see, do I have a picture of that? Sort of, right. So this is an ordinary density wave that also comes out of the inflation period, and that it's stretching, compressing. But this stuff is much faster. It's squeezing one way and stretching the other way, squeezing the other way and stretching one way, and vice versa, over and over again until you got here. And they do very different things to that photon that's traveling to us from that glow left over from the Big Bang. One of them can only make the photon get polarized, has preferred directions that it vibrates when it comes to you. So this is now the electromagnetic wave that's traveling to us from the Big Bang. It can only, this kind of wave only does this to it, but this kind of gravitational wave, which is really bizarre, swirls into the light left over from that Big Bang thing. And so what you are looking for is this sort of swirly shape as opposed to, and you can see it's sort of one where you can recognize a direction as a curl to this. Whereas this one, it's very symmetric as you go around, as opposed to having a certain handedness. And so this is the one that's the hallmark of a gravitational wave. And this is the one that you would see for other reasons that can polarize light. I mean, the ordinary polarized glasses you use would give you something like this. They would not give you something like this. So this was the prediction. And what they said on Monday is that this is what they saw, and that it actually matches pretty well. Now, this was a huge, and just blow that up a little bit, you can sort of see that handed swirliness going on here. This was a big surprise, and the reason is that we had no idea how faint and how small this polarization signal would be compared to the actual glow signal, and we were in for the long haul. We were designing, cosmologists, including the ones here at Berkeley, were designing and building experiments with a whole string of experiments planned. And the very first one that had some data was this BICEP2 one. Nobody expected that we would see the signal yet. We thought that maybe at the next 2 generations of experiments that we're going to be doing over the next 15 years, talk about scientific optimism, we had a chance of seeing it, but nobody was sure how big the chance was. They thought we might have to do another 4 generations of these experiments, and nobody guaranteed that we'd even see it then. And so it was going to be, we thought we should give it one good college try at least, go a couple orders of magnitude down, and then we were going to have to look at each other and decide, well, okay, now what do we do? But the very first project that had any data already saw it before even the second one got online. So that was a surprise, that it turned out to be too easy, or remarkably easy, that you could actually see it. In the very first factor of 3 or 4 that you went down, there it was. So that was really exciting. And just to show you the kind of plots that show up in the paper when they do this, they are plotting this. This is telling you basically what are the big splotches on the sky, and these are what are all the little fine small splotches here on the right. So the smaller the feature, the further on the right, the big features are on the left, mapped out across the sky. And the question was, how much of this polarization signal do you see? These were all the previous experiments marching their way down, not seeing anything that you can see here. This is the new result, shown here in black. And and of course the immediate questions were, did we pull signal out of noise, or are we seeing patterns here that we're interpreting a signal, which really are other noise sources? First thing you need to know is that there is one noise source that we expected, this one here. This is coming from all of the stuff in the universe between us and that distant globe. They act as they have gravitational poles on the photons that come around, and they'll put in a little bit of an effect. It's called gravitational lensing. And that one we had expected and already had begun to see. This is the new feature because the lensing has gone away there. And you can see these are the error bars, so they are giving you what they think the statistical error is in this plot. And you can see that this is not a matter of just statistical fluctuation. These error bars are very small. They can't be all the way down here, and this point can't be all the way down there. So that's good news. However, you then start to immediately ask questions about systematic errors. And I want to point something out that came, well, maybe I should ask somebody, does anybody already see something that might be worrying them about systematic errors when they look at this plot? I don't know whether it springs to mind, but, well, you're going to raise your hand. But for me and for several other people who were looking at it, we started saying, well, okay, but if this is what we expect for the known lensing, why are all these points above that line by more than their error bar? Now, if they were just above by their error bar, or if several of them were above by their error bar, and others were not, then you would feel like, okay, that's just statistical fluctuation. But if these are all above, that sounds like your target is off, is skewed off, and that would be the hallmark of a systematic error, that maybe something's wrong. So it makes you worry, because it makes you think that if this could be off by this amount systematically, how do I know that this isn't off systematically from something down here? In which case, the whole signal goes away. And then I don't have to believe it anymore, and we can all go home. And of course, it'll be very embarrassing for the BICEP2 people if that were the case. So that was the question that was immediately on our minds. We started talking to the experts in the room on Monday morning, including Adrian Lee, the professor here, who's the person who's building the really sensitive detectors on that other instrument that I showed you in that same picture of the South Pole. And he pointed out that they have a plot in the paper that looks like this, where they show you what their raw measurement is as they start, and they show you where they claim to be seeing this detection, which is below the raw measurement, and then you say, but so how did they get down to there? Well, it turns out that they had a systematic error that they identified, which had to do with the fact that their ability to measure where their polarization was in this direction versus this direction wasn't perfectly lined up. So they weren't looking at quite the same place in the sky. And so they had to account for that and fix that. And that's what they used to take you from this green line down to this blue line. Then they had to use some other corrections to get the noise level down to this line and then this line. And it's by getting down below the signal they expected that with their noise that they thought they could see the signal, because otherwise they're just dominated by the noise that they had. So that already made you feel a little bit nervous because they're having to do a big correction in order to see their signal at all. And it makes you wonder, well, couldn't you make a mistake in the correction? And couldn't that be causing the signal? So these were exactly the kinds of issues that I asked. He then pointed us to the next plot here, where they fortunately have been coming online with a new experiment, another measurement, called the Keck measurement. This is BICEP2 and Keck. And they were they were using one to test the other. And then they were saying that you see the same thing in the other one. starting to show up. And it's not as strong a signal, but something's there. So that gave him some confidence that it really was, that it was real. It wasn't just an artifact of the systematics of that particular experiment. All right, so I'm going through all this just so I wanted to give you a feel for the kind of questions that we start to ask. And it left me with an interesting moment, because how do I know whether I believe that article or not? So in the end, after reading the article and seeing all these discussions and all these, these claims that no, they take into account systematic error, and here's the level at which they thought the systematic error was playing a game, they were showing these different plots, I found myself thinking, I think it's probably right. And then I would get to confidence levels, or credence levels. I give it about, personally looking at that, I would give 56% chance of being correct. And I thought, that's pretty good for a major breakthrough, but it's only 56% chance, and we're not going to get to know whether or not they were right or not, probably for at least another year, because it's going to take a while for all those other experiments to complete enough of their data to be able to test this point, because they were all building for the future. They weren't currently observing at this level. I asked the expert, the guy who is the competitor. He works on projects that are racing with these projects. What do you think the odds are that this is right? Because I think his credence level is more important for me to ask than my credence level, because he actually knows them, he knows the work, he knows the problems. He said he thought they were 97% likely to be right. So from the paper, I couldn't tell. I was saying, I think maybe a little more likely right than wrong. But for somebody who's an expert in the field, he felt that he was fairly confident that they could be wrong in some details. So some of there could be some slight changes in the values, but that he was pretty sure that the basic effect is true. They really have seen these signals from this tiny fraction of a second after at the Big Bang that all these ripples were, that then got inflated to make this glow of the cosmic microwave background. All right, yes.
So your colleague is the competitor. Does his instrumentation involve the same systematic errors and will it require the same corrections, or is it a different methodology?
It's a different methodology enough so that they will not have the same systematics. There's also that satellite that I showed you that picture of a little bit earlier. They have a way of indirectly getting at this, which we think they may be the first people who will be able to do because they already have the data in hand. It has completely different systematics as well. So we think that we can avoid some of, it won't fall into the exact same systematics, and you will be able to cross-check that way. But it's exactly the kind of question I had too, as I was looking at this. So that's the basic story. The only thing I can then add beyond that is that if true, the implications of this are pretty big, because it's the first time that we've been able to test a theory about what was happening in this period before the glow. The glow is something like a screen. You can't see past that glow. And that could be as far back as we get to look. And that's 380,000 years after the Big Bang. What a shame. If we could never learn anything earlier than that. And yet, this could be the first indication that we're seeing the signal. It's letting us see back through that screen to that first and any fraction of a second. And maybe we'll be able to learn more about what triggered this and how did that form. So that's where the excitement is, and that's why we think that if we can figure out what 3 people should get the Nobel Prize, if this turns out to be 97% true, is confirmed at the 99% level, then we could expect a Nobel Prize in this field. And more than that, we might get a chance to learn something that you never would have expected if we can make a prediction about the very early universe. One other thing I was going to add is that now ask yourself, singular causation, general causation, causation at all, right? I mean, how does this fit into the whole causation story that John's been telling us about, and that we've all been discussing this entire class? Because it's not like we went in and we, wiggled over here, and we were able to show that that was the cause of the polarization that we got on these photons over here, right? It's a very different way of inducing a causation story. And this is one that I think we would need to work out, again, completely separately, because we have to ask, these are the stories where you come up with models and pictures of how things work, and then those models or pictures have to predict things that you would not have expected to see. And then you go out and you do all the hard work and you look for those things, and if they come out the way they predicted versus some other theory, you start to trust that theory's causal explanation more. We don't, of course, feel like we're going to come out and say, it is inflation at 98%. That's not what we're really saying. But we are saying, the bets these days are that inflation is a little closer to the truth than most of the other theories that we have, and that is a causal statement, even though it's not the usual kind of causal statement we make. It's also a causal statement about the blame for those particular photons getting this kind of polarization stuck onto them. We know who to blame, and if we're going to put somebody in prison for it, it's this inflation that did it. If this theory is correct. But it's only a one-time thing, and we don't know whether that's a general statement, except to the extent that we think that the theory that we come up with looks to us like you could generalize it to universes that we will never get to see. And so that's, it's really pushing the limits, I think, of this whole concept of causation that we've been discussing. All right, so I've been ranting for a while. And it's 3. So if anyone wants to ask questions, feel free. Those people need to leave.